Yes, a number of slides. Just fine. I don't.
It's meeting you.
I don't.
You. And you. Didn't see that coming. Well. No. That's why I'm saying in a droll kind of, oh, is this a surprise? So I got way later.
All right. Guess it's been a quarter after here, so we'll start after. Thank you for attending. Today is a talk on applications of systems engineering to UTM problem space. What we'll do is first go over some background and objectives for this workshop. Then we'll look at some operational analysis, specifically development of operational use cases, and then how that feeds into actual system modeling, functional analysis. So this is a very quick overview of systems engineering, especially model-based systems engineering. I've actually done workshops for 3 to 5 days on this, so it's very, very fast. Information on myself: I started at the Royal Canadian Navy as a systems engineer. After I got out of the Navy, I spent my time in UAV systems, working for a company that did the software for the Shadow 200 UAV as well as the Hunter UAV. I've served on a variety of standing committees, standardizations, interoperability, as well as the Canadian Air Regulations Advisory Committee for actually developing regulations for operations in Canadian airspace. I've taught courses, as I said, on systems engineering around the world, and I'm currently vice chair of InCOSI Canada. InCOSI is the International Council of Systems Engineers, and I'm currently employed as a technical solutions engineer for Kongsberg Geospatial. So the references I'm using for this workshop, systems engineering references, are IEEE 15288, 2015 version, and the InCOSI Systems Engineering Book of Knowledge, version 2, that just came out in June. The UTM references, primary references, are the UAS Traffic Management Concept of Operations, put out by FAA, UAS Traffic Management Architecture from the Global UTM Association, and the UTM Concept of Operations paper by Kopartikar and Company from June 2016. So the workshop objectives here: we are not trying to specify a UTM solution, so I'm not standing up here telling you that this is a solution to UTM. I have tried to be compliant and as much as possible with the UTM references, making sure that it's consistent. We're not breaking anything that's laid out in those documents. We're not trying to advocate a specific modeling approach. Model-based systems engineering is in fact still evolving even within the SE community. So what I lay out here is a gospel. It's still evolving. There will be other people who do things slightly differently. This is a way that has worked for multiple teams against multiple problems. And we're not trying to advocate a specific modeling tool. A specific tool that I use in general is Enterprise Architect from Smart Systems, but I've also used Rhapsody and Capella at other times through my career. All of them have pluses and minuses. So the tool that you choose to use has to fit your environment and your needs. What we aren't trying to do is simply introduce some general SE tools and techniques and put them within the context of the UTM problem. Specifically, we're trying to introduce some MBSE techniques as used against that UTM problem and trying to illustrate the advantages of these tools and techniques. So from an operational analysis perspective, what is systems engineering? So systems engineering is effectively the discipline that manages technical complexity. So in general, a systems engineer their knowledge is more broad than deep. So a lot of systems engineers have come from a specific engineering discipline, so they'll have depth of knowledge in that one area. But the power of a systems engineering is actually to know quite a lot about a lot of the disciplines that have to come together and integrate. The product that a system engineer delivers is actually a successful, smooth, low-risk integration. So we're not really delivering out some sort of product. We're bringing the products together and then creating the resulting system. And the intent is that we want that to be low risk. I think anybody who's gone through integration knows that quite often the wheels fall off there. Well, the whole product, the whole goal of systems engineering is to try to make sure those wheels don't fall off. Standard V model development, as I said, it's iterative and recursive, which means that within each one of these steps, we will iterate back up to higher level steps as we learn more about the system we're developing and refine the design or the requirements as needed. That being said, all the same steps are recursed all the way down the design chain. So from a system development, to the system development, to the subsystem development, to the actual component development, you use the same techniques from a systems engineering perspective. In this workshop, we're only looking at the left-hand side of the view. So we're not really looking at the integration and the verification and validation of the right-hand side. What is operational analysis? Operational analysis is trying to solve this problem. Many of you have probably seen this before. The number of areas of disconnect within a project. These are all areas of vulnerability to the project. So any one of these can actually pull a program right off its rails. Primary sources of the problems are how the customer explained it, how the project was documented, and what the customer really needed. So if you apply systems engineering techniques to solve those three problems, the rest of the problems that are illustrated up there are minimized or even eliminated. So what is a use case? So a use case is a term that is often misapplied. It's not just for operator interactions. It also describes the interactions of system to systems. So the term use is unfortunate in the sense that it makes people think that it's user specific, and it's not. It can be just systems interacting, and a use case is still valid. It is also not the same as a software level user story. Though if you develop your software, your system use cases correctly, you can quite often pull it apart into user stories fairly easily. Despite the word use, it applies at every level of design, not just the operational. So there will be operational use cases, there will be system use cases, there will be subsystem use cases all the way down. Properties of the use case. So the normal flow, this is how we expect the system to be used 80% of the time. The alternative flow takes a look at the normal flow and identifies anywhere in that normal flow where a decision is made or a condition is assumed. And then we have to actually define how the system operates when the decision goes a different way or the condition is not actually true, it's in a different condition. Exception flows, those identify how the system is expected to operate under specific failures. So if the system is not expected to operate, you don't have to address it. But if the system is expected to be somewhat fault tolerant, then you need to identify what faults it's supposed to tolerate and how it's supposed to operate, whether it's a degraded mode or whether there's redundancy that keeps full mode. But we need to actually identify that and say, yes, this is what it will behave like under those conditions. The last one is malicious flow. So anywhere in the normal flow where there's an opportunity for a hostile action, we should take a look and say, how do we guard against that? Obviously, things like cyber attack fall into that. Physical attack also falls into it. So how do we actually guard against those eventualities, and how do we design the system right up front for that? The primary value in use case analysis is actually edge case identification. Engineers are usually pretty good at solving that normal flow, at 80%. Where the system falls off is whenever we get an edge case. We're getting a verification or validation or operation, and we find that under certain circumstances, the whole system falls over. And when we look at it, we realize that should have been a circumstance we identified up front and designed for. So that's the real value of the use cases. So to get started, you can actually start with a very abstract diagram. So within the defense DoD architectural framework, DODAF. This is called an OV1, an operational view 1. You'll see that I refer to some military approaches through this because they actually have a history of working. So fundamentally, the system is just a great big abstract, and all we're doing is saying who's interacting with it, and what are they doing? What do they expect from it, and what do they provide to it? So this should also include what information is actually being exchanged at a high level. So an example use case template, you actually have this, actually I didn't mention, there are handouts for this, and I do have hard copies up here for anybody who doesn't have the electronic copies. But fundamentally, this is a use case template. So we have an area for the normal flow, the alternative flows, the exception, and malicious, as we call them. The rest of this isn't all that important. The only other ones that I'd say have some importance that are worth noting is the trigger, what causes a use case to actually start, and the preconditions. What state do we expect our system to be in when that trigger occurs? So, in developing the operational use cases for UTM, first thing that we did was actually just write down titles for what we think are the operational use cases we're going to need to cover. Typically, if you're doing it correctly, it shouldn't be much more than about 20. Because at each level, you'll flesh out another 20. So you'll build up the complexity through that iterative recursive methodology that we talked about. But at each level, you want it to be fairly comprehensible. So much more than 20 use cases, and you're probably starting to get too complicated. You've probably got a little bit too deep in the design at that point. So in this case, we came up with 7. I strongly suspect that as we work through them all, we'd probably get up to somewhere around 12. So I don't expect that this is a complete set. We've actually developed 4 of them, and they are in the handout package for you to review. So we've gone through that whole template and developed the normal flows, alternate exceptions, and malicious. So we've looked at routine operations, operation plan authorization. You'll see that I've scored out flight there. That's because in the handout I actually called the use case UTM flight plan authorization. And then when I was re-reviewing the FAA document, I found that they were making a explicit distinction between flight plan and operation plan, so I used the wrong terminology. So whenever you're reviewing that, please swap out the flight plan for operation plan. We also looked at training and operational development. We did not work out use cases as of yet for the emergency situations, nor the hostile actions, nor complete system use cases for system maintenance. As more use cases develop, we'll often need to iterate back into the previously developed use cases as well, and we actually have an example of having to do that. So for routine operations, this is what we have for normal flow. So fundamentally, the way we've gone through this is that at the beginning of each statement, we identify the actors that are involved, and it'll become clear why we do this in a couple more slides. So for each one, for step 1, there's a regulatory authority, and there's the UTM system. The information that is then exchanged is the regulatory authority provides a regulatory model to the UTM system. And this we do for each step. So we're trying to make each step atomic, so that there's only one set of actions that's taking place. We're trying to identify the actors that are involved. We try to keep those actors to 2. Sometimes it'll grow a little bit, but for the most part, we're trying to keep it to 2. So you'll see the first 6 steps are all about just gathering information. And then in the 7th step, the UTM system actually pulls that information together and creates what I've called the recognized airspace management picture. And this also harkens back to a military approach. In the military, you have a recognized air picture, a recognized maritime picture, and a recognized land picture. Those are all pulled together to become a recognized operational picture. But the concept's the same. So I chose to use a similar terminology because I think it actually applies quite well. From there, the recognized airspace management picture, RAMP, so it's also a nice acronym. I considered recognized UTM picture, but RUMP didn't work quite as well. But the RAMP is then used by the UTM operator to monitor the condition of the airspace. He's going to identify some non-compliances. He's then going to interact with the UAV systems and direct them to take some corrective action. They're going to confirm that they're taking corrective action. He's going to confirm that it is sufficient to address the non-compliance. Then he goes back into monitoring mode. And that's pretty much the end of the routine operations. But there's alternates. This is only one of the alternates. So in this particular alternate, we're looking at one where the non-compliance actually needs to be addressed by non-UAV traffic. So we have a manned aircraft in the airspace. He is voluntarily compliant. This is one of the definitions that the FAA has identified. They can be voluntarily compliant. And therefore, we need to say to him, okay, you've got a UAV in the airspace. For whatever reason, that UAV cannot take the corrective action. Perhaps it's an emergency UAV sending out a defibrillator or something like that. But we really need the manned aircraft to take the corrective action. So the operator now interacts with the manned aircraft, tells them, okay, we need you to take that corrective action. They take the corrective action, confirms that it's sufficient, and we're good. However, it might be a case where that aircraft is actually in controlled airspace. And if that's the case, we no longer have control. So now there needs to be an interaction with ATC. So you'll see the numbering on the side. What that's intended to do is show where it fits into the higher level flow. So in this case, that first one steps in at step 9 of the normal flow. And it tells you at the end that it goes into the normal flow at step 16. That's where it returns. But in our subsequent flow, we're saying, no, actually we have to do it in air traffic in controlled space. Now at step 9.1, we have another set of events that have to take place, where we tell ATC, we need you to do something with this guy, and we'll give you a recommended course of action. And then there's a third one here where ATC says, yeah, I don't care what your recommended course of action is, we're doing something different, we'll tell you what we did. Because in the end, ATC is the ones in control. So all this does is it very explicitly outlines what are the various conditions that we might expect, and what are the actions and interactions we expect from the system and the operators. Exception flows. So here we're looking at failures. So this is just two fairly simple ones in the sense that one is a UAV declaring an emergency departure from the mission plan due to system failure. And we actually call out the other use case here. So we have the communication that there's a problem, and then we said, okay, now we're going to go into the use case UTM operations emergency. And as I said, we haven't defined that here, but that's where we would flesh out what would we do. Likewise, could be that the emergency departure is actually due to an imminent loss of separation. So it's a collision avoidance. Again, we have to go in and deal with that in the UTM operations emergency, and we'll identify that in that use case. Malicious flow, this is where we take a look and say, okay, we could have a malicious UAV entering the airspace. It's going to do something. We have to take some action. We could possibly have a malicious manned aircraft as well. So in the first situation for the manned aircraft, we actually reach out and say, who are you and what are you doing here? They volunteer that here's who I am. And we say, okay, so you're obviously okay to be here. You're not a malicious actor. If, however, they are malicious actors, we drop into the UTM operations hostile use case. And that's where we would flesh out the more detailed scenario in there. In here, we can also identify what is the information exchange requirements at this level. So this is a very high level. So I've just pulled out one example here. This is the weather service. So what do we expect to actually be provided? We expect to have weather status and weather prediction. And we expect that to come into the system, and the system will then do something with it. And as we go down levels, we'll flesh out more detail on this. It's also quite often useful to understand how the use cases themselves interact. So which use cases use another use case? Like we've shown that the routine operations uses the emergency use case and the hostile use case. So that's useful. You can also see how it interacts with the other actors. So in this case, you'll notice that UTM operational development, it is the only one that interacts with operational authority and regulatory authority. And as we develop that, we'll see why that's the case. This is why we try to make those use case steps atomic, and we try to identify our actors. Because much as it's written in a manner that's consumable and reviewable by an operator, it now lends itself to translation into sequence diagrams, getting into engineering artifacts that we can now hand off to engineers who understand this is the interaction I actually need to have happen. So, functional design. moving towards system architecture, it's never an engineering briefing unless we have Dilbert. So we need to address the requirement. So description of system modeling. Key characteristics of a system model are they are entities and relationships. That's actually the definition of a system model. It needs to be searchable. We need to be able to put in keywords, titles, and find the objects we need, because the models can get quite sizable. It needs to be traceable, and that means that we need to be able to trace from requirements back to use cases, showing where those requirements came from, and forward into design decisions. It also helps to allow us to define other relationships that aren't just traceability, but where we will understand that certain features of a system actually rely on the existence of other features, such that later on, if there's some decision to remove a feature, we can actually do a proper operational impact. It needs to be globally modifiable. So if we change our entities or our relationships in one place, it needs to change everywhere. We can't have it where we're going back and having to change it in multiple areas. And we need to be able to create views. So we have a model, we want to create views as needed. Those views are used for analytical purposes and design purposes. We should only model as far as is useful. So this requires engineering judgment. So there are tools out there which are very good for people who are not conversant in model-based systems engineering, and they will force you to go to the same level of modeling for everything. And that's not bad if somebody doesn't actually know how to do model-based systems engineering. Once you actually get conversant and comfortable with model-based systems engineering, you'll realize that you just don't need that level of depth all the time. So it's nice to have a tool that allows you to go as deep as needed, but then whenever you know, no, I don't need to go any farther than that, because the rest of this is fairly simple, the engineers will understand this, you don't actually waste time or effort trying to generate a model just to put a tick in a box. So description of system modeling, this is just a screenshot of Enterprise Architect. What I wanted to illustrate here is this is not the model. That is a view. This is the model. Those are the entities, and the relationships are defined between those entities. You can construct whatever view you want as applicable to the analysis that you're performing. And that's the power of these sorts of tools. So whenever we pick apart our UTM routine operations, we get interactions like this. We basically get a functional breakdown, and you'll see that we've broken it down into different systems and different functional blocks. If you're starting with a greenfield architecture, greenfield design, there's infinite numbers of ways of breaking this down. If you're starting with a system of system approach, chances are you're trying to utilize some existing systems. So that will fundamentally put a constraint on you as to how you break down your functionality within the system, because you want to actually define those systems in a manner that's consistent with how they are actually implemented now, because you don't want to have to modify them or build a new system. So in this case, what we've done is we've defined a UTM HMI and a set of models that it operates out of. So one's a physical model, one's a regulatory model, one's a procedural model. And you'll see that the physical model is actually populated from an actual physical model. So all of the models that are attached to the HMI are reference models. So they're the models that are just referenced by the HMI. Everything that's actually physically in the environment interacts with the actual model itself. And that then swaps itself in effectively for the reference model. And you'll see why this is the case in a moment. But we've now got a subset of our actors that we had at the top level interacting with all of these functionalities. This is also where we can start to refine our information exchange requirements. So at this point, the weather service, if I blow it out, I don't just have prediction and status. I've also got the fact that we need what is the condition, what is the location, what is the precision, and what is the probability. And for status, we need the condition, location, and precision. Because since it's current, the probability is 100%. And this allows us now to start fleshing out a little bit at a time as we go deeper into the model, the complexity that we need to be able to support. We can also define relationships between the information items themselves. So this is where we've actually gone in and we're starting to create an information model. This information model shows that at the top level, again, we had local weather status and local weather prediction. Now we've broken them out into a little bit more. As we go down farther, we'll start to break it out further and further. And this is how we'll get to an interface design document or an interface control document, depending on how deep we want to go on each one of these interfaces. This is another good example where you stop where it makes sense. If I've got a location interface here and I'm using GPS, honestly, I'll just call out GPS because that's a standard interface. I don't need to go any deeper than that, right? If it's an interface that is non-standard or that we need to define, then you define it further. Most tools also support the generation of documentation, like the traditional documentation directly, like ICDs or IDDs, or requirements documents, design documents. Sometimes in this particular tool, you actually have to structure the model correctly to get the document to come out nicely. But it does generate the documentation as you need. So if you're interacting with a customer or a program that needs it in a more traditional format, using a model-based systems engineering approach does not usually mean that you can't do that. It just means you generate the documents. So, if we pull apart the operational training use case, so all these use cases are actually in the handouts, we found that the reason that we pulled that physical model as a reference is because in this case, we'll actually swap in a virtual example rather than the actual. So in this case, what we'll have done is we will be either playing back or inserting simulated data, and we want the system to see it all as if it was just the same as if it was connected to real systems. Now, one of the things that fell out of this is as we developed this training model, we realized that we didn't have recording in the first use case, routine operations. So again, in the handouts, you'll find that the third use case is actually the same as the first, except it's showing that iteration. Where we've added in recording, we've also added in some design notes. So one of the design notes here is, well, if we're doing recording and we intend to be able to fast forward or jump in time during playback, then chances are during recording, we not only have to record all the information coming in, but we have to record system state. Otherwise, you're always going to have to start at the beginning and play right from the start. So, but if you record system state, you can now jump forward to the next full state and then play your inputs from there. So it provides us a little bit more information that has impacted our routine operations that we hadn't considered when just considering routine. We've also identified here that from a playback position, we may very well actually take the playback and insert simulated entities. So in this manner, the two things have to be able to interact and even substitute for each other. However, from the perspective of the UTM operator over here, he can actually be interacting with it exactly as if it's the same, as if it's a real system. UTM evaluator may insert problems or may change behaviors of entities, and that will feed into that training process. But now, having constructed a view of the routine operations and then constructed a view of the training operations, we can now pull those together. So each one of those views is not too complex by itself, but now we pulled it together and started to see some more complexity emerging from the whole system. And with each one of these incremental views, we can take a look and look for consistency, completeness, and coherence. Those are really the three hallmarks of a solid design. We want to make sure that information that's flowing through has a source somewhere. If it's being generated by a component of the system, we need to make sure that the information available to that system is sufficient that you can reasonably expect it to be able to find that information, to be able to derive it or calculate it, whatever it needs to do. And obviously to make sure that we don't have different needs through the system where we're defining a parameter in one way in one use case, but differently in another one. We need to make sure that it flows through the system in a consistent manner. Operational development. So we distinguish this one because fundamentally UTM is a disruptive technology. UAS in general are a disruptive technology. So we can expect that there's going to be a lot of evolution in the near term. That means that the regulatory models that they come out with initially, chances are, won't be the regulatory models that we have 10 years down the road. So they're going to want to try to evolve those and address whatever problems are encountered. That means we need a system that actually supports the ability to trial those without having to actually put them into a real-life system. So this can leverage the playback and simulation capability by allowing us to swap out the regulatory model or the procedural model. Procedural model is UTM specific, the regulatory model is obviously ATC. So each one of these, or both, can be modified, and then we can play back recorded data with changed simulated data and say, does this make sense? Could we operate our UTM like this? Are there problems? So before committing to making either regulatory or procedural changes, we can actually evaluate what's the likely impact. And again, we pulled together all three of these now, and we've got emerging complexity. So in this manner, we're slowly building up the complexity of the overall system by taking a look at functional silos of functionality, but still bringing together the overall functionality so that we can make sure that it is consistent, coherent, and complete. The final one we looked at was operation plan authorization. And this is one where we pulled out the mission planner from the GCS, identified it as a separate role. That may or may not be true, but functionally it can be treated that way. And it interacts with a operational flight model, flight plan model. And again, we use a reference model here. And there's a number of interactions here, and as we go through the use case, we see that there's the normal flow is actually a automatic authorization. So the flight plan model there will have some sort of set of rules, likely defined within the procedural model, that it allows it to automatically authorize a submitted flight plan. And that's the normal expectation of operations. However, there's the edge cases that we talked about. What happens when it doesn't meet those rules? Well, now it has to send that information to a UTM operator and say, is this acceptable? UTM operator may or may not accept it. And if they do reject it, we need to have the information going back to the mission planner saying, it's rejected, and here's why. In addition, there might be an instance where the UTM operator looks at it and says it's not in compliance with regulations, in which case it needs to go back to ATC. Potentially, if the UTM operator isn't comfortable rejecting it, thinks that maybe this is okay, then there's an interaction with ATC as well. Make sure that they're okay with this. Can we do this? This one also had some interesting malicious scenarios that fell out. Things like denial of service attack. What's to stop somebody having a hostile act against this service, this authorization service, by simply hammering it with requests? So we had to define what happens if you lose communications. Well, if you lose communications, you have to assume your mission plan is not authorized and you cannot do it. Okay, how do we affect the denial of service? Well, maybe we start taking a historical record of who has submitted flight plans in the past and prioritize them. So if there's anybody who's submitting this a nonsense identifier, perhaps we don't, if we're under extreme traffic conditions, we don't respond to them. Likewise, any kind of hacking or things like that, there needs to be some sort of defense against those. Now, the other thing that fell out was that cybersecurity itself is not part of this system. We've assumed that, in fact, we will assume that there's some network level protection against viruses and things like that. But that doesn't mean that we can ignore every type of cyber attack. So there's some of these that would need to be addressed. Again, there's another view, functional view, UTM system. In this case, we've added in a couple of system administrators as well to get a little ways into the maintenance model, the maintenance use case. But we're starting to realize that, in actual fact, there's a lot of components here. How do we bring them all together in a successful manner that this integration is successful? That means managing all of those interfaces, making sure everybody understands who's on both sides of those interfaces, what information needs to be exchanged, and how it's expected to be used, such that we can actually affect a successful UTM solution. As a reminder, that's our starting point. So we started from something pretty simple. Step by step, we've blown out the complexity so that we understand where the complexity lies and how we can manage it. This in summary, starting with a high-level operational view. Develop the operational use cases to identify and capture major interactions. We define the top-level IERs to bound information exchanges with external actors. Used use cases to draft a functional architecture for each of the operational use cases. Refine those information exchanges, and then combine the functional architectures to define an overall system functional architecture of the system. And this is just the functional architecture. Typically from here, we would now move down to a logical architecture and then a physical architecture, but obviously there's not enough time to go into all of that. So hopefully this has been useful to you and you found it of some use. Any questions? Yeah.
I see some similarities to in what you presented to the idea of STPA, or Systems Theoretic Process Analysis. Are you familiar with that, and is it related to your approaches here?
No, I'm not familiar with it.
Okay.
As I said, I'm taking this directly from, experience has been developed over years, but it's been documented with the INCOSI CBOC, the System Engineering Book of Knowledge. So I guess I wouldn't be surprised if some of the people on that committee were familiar with that, so it may have borrowed from it. Or it might be the other way around. I'm not sure which quarter they came from.
Yeah. Well, there's a lot of similar language in systems engineering anyways, but yeah. Okay, just wondering.
Anything else?
Yeah.
Hey.
I don't know. So a lot of times with the UTM call system, but it looks more like an ecosystem. It's actually really hard to draw an actual box around the system if you're talking about it, not in a test environment. Have you thought about that at all, or how you address that with the system engineering?
That's where I started. You saw from my background, I'm not a newbie to UAVs by any stretch, but UTM has been fairly new to me in the last 18 months or so. And I was really trying to get my head around it because I was hearing UTM used in different ways for different systems that provide different solutions, and yet they were all using the same term. So honestly, this started as a personal project of mine that said, how the hell do I understand this system? So I agree with you, and in fact, that's why I think the systems engineering is very important, because I'm not implying that any one company or one system is developing all of this. What I'm saying is that, that the GCS and the UAVs, that's going to be a whole host of companies, right? But they've all got to understand what are their interfaces, what are the standardized interfaces, and the FAA and other authorities have to standardize those interfaces such that we all know, okay, this is how we're communicating. But not only what are we sending, but what's the context? How are we expecting that to be used? And that's what use cases provide context, right? Typically, I consider information exchanges to be data. Use cases are context. That then gives you information, right? Data within context is information. Until you have the two, you don't really have it. But you're right. To bring all of those systems together from all of these different providers and expect them to work together is a non-trivial problem. And that is what systems engineering is about, managing complexity. So typically, from that functional diagram, where I would typically try to draw my boundaries for my logical architecture, would be I would try to put